Dziękujemy za tę długą listę inspiracji i przykładów z polskiego podwórka, tym bardziej, że kolejna prezentacja to spojrzenie wstecz na minionych 35 lat gospodarowania wodami opadowymi w Europie ze szczególnym uwzględnieniem Niemiec, bo to właśnie z Niemiec jest nasz kolejny gość. Jak dziś skutecznie wdrażać nowe podejścia do zarządzania miejskimi zasobami wodnymi w istniejących systemach miejskich? O tym opowie pan Ulrich Dittmer z Nadrańsko-Palatynackiego Uniwersytetu.
And thank you for inviting me and for having me here. I'm going to continue a bit on what Herbert Reiseitel already presented, but I'm going to have it a bit more dry, as far as water can be dry, but it's more about engineering and numbers. When I chose this title, From Urban Drainage to Urban Water Resources Management, 35 years of paradigm shifts, I wasn't aware that time is limited. So it's a big title, and I try to focus to break it down to the time that is available. And I'll start my watch. Yeah. So this is the content. I first want to talk a bit about paradigms in stormwater management in particular, and then just look back at where we come from and look ahead where we might go, and then close with some final remarks. So let's start with paradigms in stormwater management. Actually, what Herbert talked about was a lot of paradigm shifts. We often hear this word paradigm shift if something new is coming up, some new ideas. So actually, I asked myself, what is a paradigm? And of course, I didn't ask myself, I asked an AI. And Gemini told me a paradigm is a shared set of assumptions, concepts, values, and practices that constitutes the framework of viewing reality and solving problems within a specific group or discipline. So it basically is, I think most important is the term assumptions, and it's basically the way we see and do things in our discipline. That's our paradigms. We have theories that we check and develop and redevelop, but behind all this, there's the paradigms. There's things that we don't discuss. And that leads us to the next sentence, that paradigms act as subconscious filters. And that's important, they are subconscious. That's the problem. We cannot actively change them because we're not aware of them, because they're subconscious. So then how do paradigms shift? If we announce a paradigm shift, we have to know that there's something going wrong and we want to do something. I tried again with the AI, but the result was not nice, so I put it in my own words. When a paradigm produces unfavorable results, it may undergo a paradigm shift, which is a fundamental change in basic assumptions. And what does it mean for stormwater management? Like in physics, it's clear. You do an experiment and it's completely, the result doesn't go together with anything you expected, so you have to change your paradigms. But how is it in urban drainage? I like the talk of the mayor this morning because he said it would be nice if we could monitor everything, parameterize it, have numbers and know where we go and assess what we're doing. But actually that's not the case yet. So we don't have a clear indication of a failure of old paradigms. And the other thing is that our observations are incomplete. What we do has many impacts on biodiversity, on many aspects of environment, and we don't have the whole picture. So we cannot really see is what we are doing good or not, and in which way should we change. So it's more a consolidation of negative experience, which may induce or trigger a paradigm shift. And the question is, as everything is so fuzzy and we don't know exactly where we come from, where we go, are we moving in the right direction? And I think that is important with any paradigm shift. And if we want to know if we're moving in the right direction, we first have to look back at where we come from. And so I wanted to take a look back 35 years. Why exactly 35 years? Because that's when I started my university studies, but that's not important to you. But in the early 90s, there was a lot going on, at least in Germany and in some other EU member states. And I have this very nice reference, this stormwater pollution control report that compared stormwater pollution control measured all over Europe. And there was one more thing I wanted to say, but I just forgot, but it's not that important. So this report states that in practice, there are some paradigms. It doesn't say it explicitly, but it's more, if you read it, you find this, that urban areas have to be drained fast and completely. That was the paradigm at that time. The main concern regarding water pollution is combined sewer overflows. So if we don't have a combined systems, we don't have a problem. Because, and that's the third one, pollution of surface runoff is no problem in general. So that was the way of thinking at that time. I'm happy that Richard is nodding. And the consequences are that underground drainage systems were everywhere, because that's fast and efficient drainage. We want to get the water away. And then there were some regulations in some member states about CSO, but there was nothing on stormwater. And even CSO regulations were based on dilution, because we assumed that stormwater in itself is clear. But this report also states that there are some developments going on in the early 90s, and that these paradigms are increasingly being questioned. And one new paradigm was, what Herbert already mentioned, that we could manage the rain where it falls, like do source control. And that source control measures can substitute conventional drainage with lower environmental impact and at the same service level. So the goal was to reduce runoff, keep the water where it is, and do something with it. But what? The main idea was building infiltration systems or bioretention. Yeah, water is retained for subsequent infiltration. And the design storm, or the idea was to have it at the same service level. That means design it for the same rain intensity as we would do with conventional systems. So we can completely replace the existing conventional system by something new, more nature-based. Or if we build a new one, we don't even build the new drainage, the conventional drainage system. We just build these type of swales, retain the water, and let it infiltrate. But this requires around 10 to 20% of the connected impervious area. So that was the idea. That means the scope, what I marked here in this blue-grayish box, that's the scope of drainage. And that's the same for conventional systems or nature-like systems. The idea is up to a certain design storm that is around 5%. It could be 3, it could be 10 in some areas, depending if you're in a city or in a less densely populated area. And water shouldn't leave your system if you don't reach this 5-year event. And this also is the same for the nature-based systems. So the scope is the same, it's just a different type of technology or hardware, let's say. And once the water leaves our system, it's not our job anymore. Somebody else has to take care of it. But in the following years, there was more and more discussion, probably triggered by fear of climate change and more intense storm events. And urban drainage engineers became aware that we also, it's too easy to say that's not our job. We have to handle this, and we have to work together with people that are managing the surfaces, like city planners, greenery planners. We have to get an interdisciplinary approach, and the results were, Herbert showed a lot of them. This is just one simple example of a multifunctional area. It's a square that can be flooded, and of course it's not just a flooded square. Below the square there's still a drainage feature, so we can retain the water there and have a multifunctional area. But we still have to go further. What happens if this comes to a limit and we have more extreme events, and how do we mitigate damage in these cases? You're all aware, I saw the Sculgo stand here outside, that now we go up to the 100-year event and calculate this and give advice to private property owners how they can handle or protect themselves against flooding. So the scope is much broader, or got much broader in the 90s. What you see here on the right side is a very famous picture that is often used in Germany. It shows the 3 levels of intensity of storm events, of severity of storm events, and that it has different types of systems we need or different measures to handle them. Yeah. So stormwater management cannot stop a design storm. It must apply a wide range of different measures, and it requires an interdisciplinary approach. I think that was all touched already in the previous presentation. And it is a joint effort of various stakeholders. So it's the drainage engineers, it's the urban city planners, it's politics, and it's also the private property flood protection that is necessary. Parallel to this, there was another tendency, another, let's say, questioning of our goals, and that was led more to the urban water balance. So one is these extreme storms that we talked about, heavy rainfall, but on the other hand, what happens with the day-to-day rain event? So there was this additional goal that to minimize alterations on the natural water balance. That's a new goal that came up like 10, 20 years ago, to reduce the impacts on flow regime on urban waters and to reduce heat island effects. You all know, as was already said, that in our cities, this is our numbers for Berlin, so the majority, but it's the same in every city, the large part of the flow is, of the rainfall is converted into runoff, only a smaller part is infiltrating, and roughly the same part here, it's 18% infiltrating, 20% evapotranspirating. But this is the natural system. That's where we come from. So it's a huge alteration. If an area is urbanized, the water balance is completely changed. And now we want to go back to this pre-development state. That is the idea that we want to go to, so to have low alterations compared to the previous system. But how can we do this? Bioretention, infiltration would just increase the groundwater recharge. It would not increase the evapotranspiration, so we need to do something different. And that's where, for example, green roofs come in. This is a nice picture, looks like a garden, but it is a green roof. Or we can store rainwater and use it for irrigation. Because if we put it on the plants and the plants evapotranspirate it, then again we have evapotranspiration. So that's another idea, just using runoff, storing it, and using it for irrigation. And I just mentioned here that the keynote before, because there's a lot of nice pictures on that. So if we go back to this picture, we now have to add a new column. Because it's not only about events becoming more and more severe and more extreme, we also have the water balance that we have to consider. And in my view, to my knowledge, this is basically the up-to-date modern way of doing stormwater management, considering all this. But there are still challenges ahead of us, and one that is highly delicate is the limitation in dense urban areas. So how can we do this in an existing urban fabric? If we need 20%, look at this picture, it's taken from one of our study sites in Berlin. If you need swales, 20% of the impervious areas, where do you find them? It even gets worse if you look underground and look at the existing infrastructure that is already there. So then there's no space left, or hardly any space left. But the problem, why do we have to sacrifice 20%? That's because we want to replace existing systems, to disconnect impervious areas completely. What if we change this? I would also call it a paradigm, but the word paradigm shift in this context seemed a bit big to me, so I put a question mark behind it. But for me personally, it was a paradigm shift when I thought of it the first time, that we base design on the extreme events, on the 5-year event. But what if we do the design on the water balance and have it complementary to a storm sewer? So not as a substitute, but complementary. This would lead to hybrid gray, blue, green infrastructure systems that make the best of the existing system and just add something in addition. There's a nice picture on the right. That's the Sacramento State University, the rain garden where they infiltrate the water from the roof. I was there at a research stay, and I made this photo, sent it back to a colleague, and this colleague said, oh, this must be a pretty small roof if this surfaces, if this is large enough for infiltration. And I thought, why is it so small? And it's simply because they don't want to handle the 5-year storm or any heavy storm event. They want to handle 85% of stormwater. That's their goal. And this leads to much smaller systems. Of course, it requires an existing stormwater sewer. The overflow goes to the stormwater sewer, and up to this 85%, you infiltrate. We tested this application for Berlin, and it resulted that we only need around 1% of the impervious area to design our biofiltration systems this way, so much smaller. And this would open new possibilities, like what I show here on the right is a concept for bioretention and harvesting systems. So if we have these smaller swales, we can infiltrate directly, then the water is treated by filtration and then stored underground and use it for irrigation. So this would be a way to handle this water balance in urban areas. But still, weather extremes are more than just water balance and extreme storms. We also have to consider droughts that are becoming more and more severe. And so I extended this picture to the left, thinking about extreme drought events. So what can we do there? If you remember the picture that I showed before, having this infiltration and storage, this works up to a certain level, but if you want to prevent extreme droughts, your tanks become larger and larger and larger. It's just too expensive and you don't have the space for these tanks. So we need something different. So the problem is the large storage volume that we need. The solution might be if we combine our stormwater storage with some continuous water source. And such a continuous water source could be lightly polluted gray water. That was done in one project by a colleague of mine from our university in the Interest-I project, funded by our research ministry. So from the building you see behind, they disconnected the showers and mixed the showers with a runoff from the roof, and stored and treated it in a retention soil filter, and this worked pretty well. But again, we have a limitation. How do you do this in existing systems? Because this requires gray water separation on the household level. So it works in a new development, but what do you do? How do you retrofit an existing system? And this is where we get to the next stage. That's a new project that is currently running that we're doing together with Retentia, the Desire Water project funded by the EU with partners from many different countries, and this is just one of the demo sites that we use. And what we do here is we combine runoff from the roof with water reclaimed from the combined sewer in the city. So the water is pumped up, treated again in such an biofilter system, and then mixed with stormwater and used for irrigation. So this is a circular water management, and this would even work under extreme droughts. The large-scale feasibility is still somewhat open, that's why it's research, but we are quite confident that there is a market potential that we can develop solutions that are ready for the market. So finally, this is what I would consider the broad picture. I focused here only on design goals and design parameters, because I think that is how paradigms are translated into engineering practice. And I will close with some final remarks. It looks very nice, but I left out some crucial aspects due to time and because they're getting too complicated. Yeah? I did not discuss quality here. There's a lot of quality issues to be discussed. Receiving waters, what effects do we have on receiving water, and the drainage and groundwater interaction. I all left this aside here. It's still, that doesn't mean that it's not important. And we have large challenges and risks. And one risk that I'm very concerned about is that it's very nice having technical decentralization, but it has to be accompanied by organizational structures that are adequate for this. At the moment, we observe in Germany more and more decentralization that is not controlled at all, so it's more or less like not doing anything anymore, because if you don't control it, people won't do it unless they are highly inspired and intrinsically motivated. Yeah. And another thing is the limits of integrated planning. Herbert already mentioned it before, that so many people have to work together, but what is integrated planning? A student once said, when I asked him, that it's the synchronization of planning processes of different disciplines. And perfect synchronization is easily reached when nobody moves. And this is sometimes the case, so it is a danger. And some final remarks on paradigms. Why do paradigms fail? Either because they produce unforeseen results. Like in the old days, burying streams, urban streams, was a good idea because we have more area to work on. But now we see that cities without water are not really nice and are not livable. Or we have shifting expectations of society. There was one boom of when people wanted to bathe in urban streams. Years before, everything was too expensive. They were not willing to pay for any stormwater treatment, and then they want to bathe in the water and are willing to pay all of a sudden. So we have to handle this. Or there are new drivers, like climate change is not new anymore, but it wasn't known like 35 years ago, or not that considered. Or we have technical developments, maybe things that seem completely unfeasible are feasible all of a sudden. But we have to be aware that paradigms are inevitable in research and practice. So if we overcome if there's a period of paradigm shift, everyone thinks, oh, that was the old thinking, but now we have the new view and we know reality, but we only replace old paradigms by new ones. They're always there. Yeah. And we should try to be aware of them and continuously question them as far as possible. And they should be shifted actively if there is good reason, but only if there is good reason. Just novelty for the case of novelty is not a good idea. Yeah, doing something different because I want to do it different, if there is no reason for it, then leave it. Yeah. And last but not least, stormwater infrastructure is highly conservative due to the long service life of our systems, and we have to be aware of this. So if we have a paradigm shift, want to do everything new, we have to be aware, and Herbert already said it, we need a long strategic plan. We cannot change things today and then they're different the next. So thank you for your attention.